All right, welcome back. This is part 2 of the previous lecture dealing with our introduction to power series. Let's just pick up right where we left off. And in the first part, we got a lot of the theoretical aspects out of the way, basic definitions, terminology, what power series are, how we're going to use them. In this part, we'll jump straight to the examples. Given a power series, finding the radius and interval of convergence. Now, before we get to those examples, let's just briefly review where we left off. For a power series, we have this theorem telling us there's 3 possibilities for the convergence of it. The first, the power series converges only at the single x value, being the center, A. The second possibility is there is an interval of x values for which the power series converges. The third possibility is that power series converges for every value of x, all real numbers. Now keep the remarks in mind down there. We're typically going to apply the ratio test. That's why earlier we said the ratio test is extremely useful since it applies now to power series. And the second remark is rewriting your absolute value inequality as that compound inequality. We get the endpoints of the interval, a minus r and a plus r. We're going to have to check if our power series converges or diverges at these endpoints. With that in mind, let's get straight to a few examples. We'll go through part A together, and I'll give everyone an attempt at parts B and C. Okay, so the question asks for the given power series, find the radius of convergence. That's what we've been denoting as capital R. And we're also going to find the interval of convergence. All right, again, the biggest tip I can give is we're going to generally always apply the ratio test. And regardless of the type of power series you have, either x to the n or x minus a to the nth power, we're going to use our exponent trick when we increment n to n plus 1. We can split up something to the n plus 1 power as that quantity to the nth power times that quantity to the first power. Specifically, x minus a to the n plus 1th power can be expressed as x minus a to the nth power times x minus a. If you're at all uncomfortable with that, multiply the right-hand sides together. Since it's the same base, you can add the exponents. N plus 1 gives you that exponent on the left there. All right, let's go ahead and get to part A. We're going to think of the whole term as being a sub n when we apply the ratio test. Now there's 2 parts for now a power series. The nth or general term is made up of the coefficient c sub n, which here is 1 over 2 to the n, and then it multiplies a power of x here, x to the n. Well, let's just consider that all as our general nth term for a sub n as we would have applied that to the ratio test. Now to make some of the manipulations easy, let me move that x to the n into the numerator. So let's write a sub n as x to the n divided by 2 to the n. And recall with the ratio test, we look at the ratio a sub n plus 1 divided by a sub n. And then when we're dividing fractions, we can multiply by the reciprocal. That's why we wanted to express a sub n all as a single fraction. All right, if that is our a sub n, we need to increment and take a look at a sub n plus 1. So in that expression, replace all n's with n plus 1. There's an n in the numerator, and then an n in the denominator. And we're going to make use of our exponent trick. We're going to rewrite x to the n plus 1 as x to the n times x. And similarly, for 2 to the n plus 1, we'll rewrite that as 2 to the n times 2 in the denominator. All right, we have our 2 terms, a sub n plus 1 and a sub n. We now look at the ratio of a sub n plus 1 divided by a sub n. Recall that we have that for the ratio test that ratio within absolute value. Here, it is absolutely crucial to keep the absolute value. The reason for that, while 2 to the n is a number, positive number, x to the n, or x, that is a variable, and variables can take on negative values. Absolute value of a negative quantity becomes positive. So we can't necessarily get rid of absolute value signs around any variable quantity. All right, now if we divide by multiplying by the reciprocal of a sub n, we can see there's a factor of 2 to the n and x to the n that cancels out between those fractions. The whole thing within absolute value just simplifies to x divided by 2, and we can apply some properties of absolute value, individually take the absolute value of numerator and denominator. Absolute value of 2 is just 2. We have to keep the absolute value around x there, since x is a variable and it could be negative. All right, so what we get for our ratio here is absolute value of x divided by 2. Now I want to point out here, for some things that we'll get to in parts B and C, notice this end result for the ratio is independent of n. There is no index n that appears anywhere in that final result. That's going to make it very easy to get to the next part of applying the ratio test. Recall, for the ratio, we take a look at the limit as n approaches infinity. So if we do that, we now have our ratio within absolute value. We take a limit of that as n approaches positive infinity. That's what we defined with the statement of the ratio test as L. And what we find, the value for L, or the limit here, since the ratio was just absolute value of x divided by 2, there is no n in that expression. The limit here is very simple. As n increases to infinity, this expression remains constant. So the limit is just absolute value of x divided by 2. Now, if you recall the possibilities for the ratio test, the ratio test says your your infinite series converges absolutely when the limit is basically less than 1. So for us, what we want to require for our power series to converge is we want our value for L, which we found to be absolute value of x divided by 2, the limit of the ratio as n approaches positive infinity. We want that absolute value of x divided by 2 to be less than 1. All right, and that basically gives us our interval of convergence. We can rewrite that inequality, multiply 2 to both sides, and we get the simpler looking inequality. Absolute value of x is less than 2. So what we find from how we were expressing intervals within absolute value, the number 2 on that right-hand side, since we have absolute value of x by itself on the left, that number 2 is the radius of convergence. We can rewrite that absolute value inequality as the compound inequality, all values of x that are strictly between -2 and +2. The center point for our power series here is 0, so we can go 2 units from our center, 0, in either directions. 2 units to the right to reach +2, 2 units to the left to reach -2. All right, now we're pretty much done. By applying the ratio test, we get both by rewriting our inequality solved for the absolute value of x. We get our radius of convergence as 2, and we basically get our interval of convergence. Now, we're not quite done, because if you recall the remarks we mentioned at the beginning of this part 2, we mentioned we have to check individually what happens at the endpoints. Here, the endpoints are x equals -2 and x equals +2. Our power series might converge at one of the endpoints. It might converge at both of them, or the power series could diverge at both endpoints. The previous theorem doesn't guarantee that, but we have to check. All right, let's go ahead and individually plug in x as those two values. First, x as +2, and then x as -2. Now, again, this might be new. We're going to be transitioning to thinking of power series as representing functions. And functions, we usually plug in something for x. So pretty much in your power series here, there's only x to the n that appears within the summation sign. We're going to plug in that x with the value 2. Notice if you do that, you get 2 to the n, but your coefficient c sub n is 1 over 2 to the n. If you simplify that, 2 to the n divided by 2 to the n, any quantity divided by itself simplifies to 1. So what we get here is our infinite series where the general term is always 1. I just think what happens as you add up more ones, 1 plus 1 plus 1 plus 1 plus 1 forever, that's just going to keep growing and growing. So kind of basically, if you want to be more technical, you can tie this back to looking at the formula for the partial sums, S sub n. You might be able to find here the nth partial sum, where the terms are all 1, comes out to be n. Think of 1 plus 1 plus 1 plus 1 n times. That come out to n. And what you find is this diverges. Maybe more simply to apply the divergence test, since the term 1, its limit as n goes to infinity is not 0, this definitely has to diverge. So that might be a more basic or quicker way to see that this power series, or sorry, infinite series diverges. All right, so at the endpoint x equals 2, our power series diverges. If we repeat this, plugging in the left endpoint, x equals -2, just be careful with parentheses. You'll get -2 to the nth power, and -1 raised to an nth power could be positive or negative. If you take the nth power of each part, take the nth power of -1 and the nth power of 2, you can get the 2 to the n's to cancel out, but you're left with -1 to the n. And that was something we saw earlier, is also a divergent infinite series. So what we find here, our interval of convergence is the interval strictly between -2 and 2. Our power series diverges at both endpoints, -2 and 2. So we want to include with brackets in this interval either -2 or +2. All right, most of the work here was applying the ratio test. When we take a look at part B, that's going to, again, be most of the work. So at this point, pause the video and give yourself an attempt at part B. Pretty much apply the ratio test. We'll check in a few minutes. All right, welcome back. Hopefully you were successful with this, but let's go through it. I'm going to put up most of the work here, since I think you're probably getting comfortable with applying the ratio test by this part of the course. We're going to take our nth term, a sub n, to be the power of x minus 2, as well as the nth coefficient, c sub n. So a sub n, we'll define it to be x minus 2 to the nth power divided by n plus 1, writing that as a single fraction. We can again increment, replace all n's with n plus 1. And there's not a whole lot of different manipulations that appear here. We can use our exponent trick again to rewrite x minus 2 to the n plus 1 power. We split that up as an nth power and a first power of x minus 2. In your denominator, n plus 1 just becomes n plus 2. We can jump down below to taking a look at the ratio of a sub n plus 1 divided by a sub n, again, in absolute value. Use your usual trick here, divide by a sub n, multiply by its reciprocal, and what we find is the x minus 2 to the nth powers cancel out. We can't cancel and remove the absolute value around the remaining x minus 2, since again, x is a variable, it could be negative. So we keep absolute value around x minus 2, but since n is positive, we can rewrite the remaining fractions involving n as n plus 1 divided by n plus 2. Now the previous example, part A, our ratio was independent of n. Now we have a result for the ratio that does depend on n. All right, if we take a look at the limit of that, the limit as n goes to infinity of the absolute value of that ratio, we only need to look at the part that contains n. N is approaching infinity, n is changing, incrementing one value at a time. Right now, even though x represents a variable, x is not changing for this limit calculation. So what we can do is, you might recall from your first calculus course, you can bring constants out in front of limits. So we can pull the absolute value of x minus 2 out front as a factor and just look at the much simpler looking limit, the limit as n approaches infinity of n plus 1 divided by n plus 2. That has a very simple limit. If you want to be technical, you could apply L'Hopital's rule. Hopefully you can quickly see, since the highest powers of n are equal, the limit should be the ratio of leading coefficients, 1 over 1. And we find that our value for L, the limit, comes out to be absolute value of x minus 2 times 1, which is just absolute value of x minus 2. All right, so at this point, we're basically done. To make a conclusion on the values of x for which this power series converges, recall from the ratio test, we want our limit L to be less than 1. So what we require is now absolute value of x minus 2, our limit, we want that to be strictly less than 1. The 1 on the right-hand side of that absolute value inequality, that is our radius of convergence. And if you rewrite that absolute value inequality as the compound inequality, values of x that are between 1 and 3, we basically get our interval of convergence. The only thing we need to check to finish and correctly answer the question is, does our power series converge at either endpoint? Does it converge at x equals 1? Does it converge at x equals 3? Let's check individually. If you plug in x equals 3, notice within the parentheses, you get 3 minus 2, which is 1 to the nth power. 1 to any power, 1 to the nth power is just 1. But what we're left with is the c sub n, the coefficient, 1 over n plus 1. Now, this is a slightly altered version of what we called earlier the harmonic series. Basically anything with the term 1 over n plus 1, that usually represents the harmonic series. All right, and you might recall that the harmonic series is divergent. So at our endpoint 3, our power series turns out to be divergent. Now, if we plug in the left endpoint, x equals 1, be careful, you have within your summation sign 1 minus 2 to the nth power. 1 minus 2 is negative 1. So what we have is negative 1 to the n, coming from the variable part. Negative 1 to the n is an alternating term. And what we get now, rather than the harmonic series, plugging in x equals 1, this specific infinite series that we get, that was what we called and defined as the alternating harmonic series. Now keep those two examples in mind, the harmonic series, while the terms get smaller towards 0, actually diverges, maybe a little counterintuitive. But what we saw with the alternating series test is the alternating harmonic series converges. So at x equals 1, we have here a convergent infinite series. So we can modify our interval 1 to 3. It diverges, the power series diverges at x equals 3. So that for the interval remains excluding 3 with parentheses. But we can include the value 1. So we change the parentheses to a bracket. So we find, to answer our question, the radius of convergence is 1. The interval of convergence is values of x less than 3, but greater than or equal to positive 1. So our interval there is 1 to 3, where we include 1. All right, let's take a look at the final example, part C. This one I want to give you an attempt at. Maybe now you're feeling more confident applying the ratio test. But like as usual in a mathematics course, we go through examples, build up your confidence, and then the last example, we crush your confidence. I'm just kidding, but there's some complications that occur with this. So give this an attempt. We'll check in a few minutes, getting to kind of the usual point I consider students to maybe get stuck. So give this an attempt, and we'll check in. All right, let's wrap up part C here. This will basically be the final example for this first lecture on power series. So this seems pretty straightforward. You might recall some properties of factorial, which we're going to use here. So we have as our nth term, a sub n. Write that as a single fraction, x to the n, divided by n factorial. We increment, replace n with n plus 1. And we can again use our exponent trick to rewrite x to the n plus 1 as x to the n times x. We use our factorial trick in the denominator to rewrite n plus 1 factorial as n plus 1 times the previous factorial, n factorial. Again, go back and review when we introduced factorial, specifically when applying the ratio test. We can now form our ratio within absolute value of a sub n plus 1 divided by a sub n. Usual kind of tricks here. When you divide by a sub n, multiply by the reciprocal. Hopefully that's a habit that you're already using or in the habit of using. And notice you can simplify by canceling out x to the n's and the n factorials that you got from the factorial trick. And as we saw them before, we can rewrite this taking absolute value of the remaining numerator and denominator. N is always positive. Notice our indices start from 0 and go upwards to positive infinity. However, x, we're not sure if x is positive. X is a variable that could take on negative values. We have to keep the absolute value around x. So we get as our ratio within absolute value to be absolute value of x divided by n plus 1. Seems pretty straightforward. Since you're all experts on applying the ratio test, if not, you should be. It's extremely useful for the rest of the calculus sequence and certain science and engineering courses that make use of power series. We apply the conclusion of the ratio test. We take a look at the limit as n goes to infinity of that ratio. Now this one is a little bit different, but maybe it's simple to see the limit value here. Notice we only have n's in the denominator. So when we take this limit as n goes to infinity, Like before in part B, we can bring the absolute value of x in front of the limit. Right now, only n is changing. X is a constant. And the remaining limit, the limit of 1 over n plus 1 as n goes to infinity, notice your denominator is getting bigger. When your denominator gets bigger, the fraction gets smaller. So 1 over n plus 1, that approaches 0 as n approaches infinity. And what we find here is a very simple limit. Our limit, L, comes out to be 0. And at this point, I feel pretty confident that you probably applied the ratio test up to here, and then you're left scratching your head, what does this mean? Well, this is a little bit different. What we have here is a limit that is independent of any value of x. So in other words, this limit comes out to equal 0 from the ratio test for all values of x. And what that means is our limit will always equal 0, which is less than 1, for all values of x. And recall from the ratio test, when your limit is less than 1, your infinite series converges absolutely, and we saw that absolute convergence implies convergence. So what we find here is that our power series converges for all real numbers x. Or in other words, our interval of convergence is all real numbers minus infinity to positive infinity. Now, to answer the question about the radius of convergence, basically this is a power series centered at 0, since our summation contains only x to the n. And what we find here is our radius of convergence is basically infinity. We can go infinitely far to the right from 0 and infinitely far to the left from 0. All right, so that's basically the end of our first lecture on power series. This example in part C that we still have up here, this is going to, as it turns out, be a very important power series, but I kind of don't want to give too much away. We'll save that for the following lectures.